Black holes, with their enormous masses and insatiable hunger, the gravity monsters are undoubtedly among the most bizarre entities we find in the gigantic expanses of space. Most everyone has heard of black holes. What not everyone knows, however, is that these mass monsters also have cosmic counterparts, so-called white holes. Well, at least in theory, because despite intensive research, experts have not been able to prove the existence of these breathtaking objects. But this may have changed now. A few years ago, experts witnessed a remarkable event that perfectly matched the presumed characteristics of white holes. But what is the background of these breathtaking formations? And what unexplained phenomenon were the researchers confronted with at the time? Stay tuned and make up your own mind. Want to learn more about the groundbreaking discoveries and fascinating spectacles in the cosmos on a regular basis? Then remember to subscribe to Simply Space and click on the bell to stay up to date from now on. By giving us a thumbs up, you're showing us that we can keep you engaged with the content of our videos. Black holes. They are places of no return. Nothing that has passed the event horizon of a black hole can cross it again from the inside to the outside. No radiation, no information, and certainly no matter is ever able to free itself again from the captivity of a black hole. This fascinating and frightening property is due to the incomparable compactness of black holes. Since the mass of black holes is concentrated in an extremely small volume, a tremendous gravitational force prevails in their environment, transforming the objects into cosmic omnivores. However, there are also enormous differences in the black holes. According to some theories of string theory, tiny black microholes could exist in the vastness of the universe. In contrast, stellar black holes are much more imposing. These are formed when a massive star has reached the last chapter of its life. When the nuclear fuel is exhausted, the celestial bodies collapse, ejecting their outer layers in a glowing supernova. At the same time, the remaining stellar core collapses into a stellar black hole due to its gravitational pressure. Wondering how the much-quoted compactness of these objects translates into reality? Let's consider the following example. If a stellar black hole had the same mass as our Sun, its event horizon would have a diameter of just about 4 miles. To put this in perspective, the diameter of the Sun is 230,000 times larger. At the far end of the spectrum, again, are supermassive black holes. These trump the mass of our host star by a factor of millions or even billions. Although we now know that supermassive black holes decorate the centers of galaxies and play a fundamental role in their evolution, they are still overshadowed by some big question marks. For example, we currently know neither how these mass monsters form, nor how their influence on galaxy evolution plays out in detail. In view of their frightening characteristics, one could think that black holes embody something like cosmic destruction machines, which destroy everything completely. However, this is only partly true. In truth, beyond their event horizons, black holes behave like ordinary bodies of mass. For this reason, the gravity monsters can be orbited by other objects on stable orbits without any problems. Although the masses of black holes are often beyond our imagination, they are invisible to the interested eye of researchers. Thus, they do not emit observable light or other measurable radiation. So, to detect a black hole, experts must look for the effects that the entities exert on the objects around them and their white counterparts. You may be wondering why we are starting today's video with an overview of black holes. There is a good reason for this, because in fact, black holes and white holes share many fundamental characteristics. The central point where the two entities differ drastically is their direction of passage. While black holes absorb everything that comes too close to them, their white counterparts incessantly repel mass. Consequently, it's impossible to cross the event horizon of a white hole from the outside to the inside. To accomplish this, the object in question would have to move faster than light. However, this is not the only point of difference between the two entities. In contrast to black holes, The existence of white holes has not yet been proven. Although they are considered as plausible mathematical solutions for the equations of general relativity, this fact does not automatically mean that they really exist. Consequently, there are also different assumptions about the properties and background of white holes. One assumption is based on the fact that they are black holes which run off in the opposite direction to the time axis. Another theory assumes that black and white holes can create a wormhole together. The matter, which is devoured by a black hole, would be spat out thus in another region of the cosmos, possibly spatially and temporarily, by a white hole. Some experts believe that the astronomical objects had a significant influence on the birth of the universe. Thus, it's conceivable that even the Big Bang itself can be regarded as a white hole or as an effect of its existence. Mysterious gamma-ray burst. But will we one day finally succeed in detecting a white hole? The surprising answer to this question is, we may already have done so. But let's take it one step at a time. In 2006, NASA's SWIFT satellite transmitted the most puzzling data imaginable towards Earth. Shortly after the transmitted information had been sighted, it was clear something unbelievable had just happened in space. In detail, an incomparably intense gamma-ray burst had occurred, which lasted for 102 seconds. For comparison, normally such eruptions last only between 2 and 30 seconds. Thus, the event, which was given the scientific designation GRB 060614, started a new fundamental discussion about these unique energy bursts. The exact background of gamma-ray bursts is not completely clear. And also, the first discovery happened completely by chance. The first gamma-ray flash was observed in the summer of 1967 by the Vela satellites of the USA. Actually, these satellites were only supposed to detect above-ground atomic bomb tests. The fact that the detected rays came from the far reaches of the universe only became clear during a new data sighting in 1973. But back to the 2003 event. Before this puzzling discovery, experts had assumed that such intense gamma-ray bursts were caused by the birth of a stellar black hole. Consequently, such a process would also have to be accompanied by a detectable supernova. Shorter bursts would in turn have their origin in the merger of neutron stars. The problem confronting the researchers was the fact that there was no trace of such a stellar death. Rather, the spectral delays were typical of short gamma-ray bursts. But this was in stark contrast to the actual duration of the event. In December of the year of discovery, this was again followed by a publication in the journal Nature, in which the burst was classified as a new hybrid form. Basically, this includes long gamma-ray bursts, but occurring without an accompanying supernova. In the same breath, an exciting hypothesis about the background of the discovery has also been put forward. It might have been the first observation of a white hole. However, whether this exciting conjecture really corresponded to reality is still debated today. It is certain that the origin of the eruption was located in a distance of 1.6 billion light-years in the constellation Indian. Basically, however, the observation at that time behaved as one would typically expect from a white hole, a huge, unstable fountain of matter and energy that disappears again shortly after its appearance. A futile search? In light of this exciting observation, one might think that the final discovery of white holes is only a matter of time. In this respect, however, some experts paint an extremely sobering picture. The second law of thermodynamics provides us with the background of this not very pleasant news. This states that the entropy in the cosmos must always remain the same or increase. This fundamental state variable of a physical system increases with each spontaneously running process, as well as with the supply of warmth and matter. Conversely, this means that entropy can only decrease if the system releases matter or heat. In a self-contained system, in which no exchange of matter and heat with the environment takes place, entropy can therefore not decrease, a principle which unfortunately cannot be reconciled with the properties of white holes. Since these incessantly eject matter, the total entropy of the closed system would decrease. Nevertheless, We find also here an astronomical loophole, which could make the existence of white holes possible nevertheless. A rare collapse of entropy would lead to a temporary reversal of time and to the creation of a white hole. However, this theory too is accompanied by a big downside. In such a scenario, the object would disappear in the course of an enormous explosion, as soon as time takes its usual course. Possibly, it was just such an event that paved the way for our universe in the first place. Since the Big Bang and white holes share such exciting mathematical similarities, some researchers believe it's possible that the birth of the cosmos was in fact the impact of a white hole. It is quite understandable and humane to delay death as long as possible, to wish our loved ones a good, healthy, long life. Do we limit ourselves to this demand, or do we want more? In quite a few books, journals, and at least one video on the internet, this existential matter is discussed. The desire for immortality is as old as human beings. This topic was mentioned again and again in the oldest known mythologies and epics. Both Gilgamesh and Prometheus sought to achieve their ultimate goal of immortality. In almost every culture, there is a similar narrative about the quest for immortality. Does time really flow? In Albert Einstein's theory of relativity, time is intertwined with the three dimensions of space, forming a four-dimensional space-time continuum, a block universe that includes all past, present, and future. Einstein's equations represent pretty much everything in the block universe. As it was from the beginning, the initial conditions of the cosmos determine what happens next, and no surprises exist. They just seem to happen. For us believing physicists, Einstein wrote in 1955, a few weeks before his death, the distinction between past, present, and future is only a persistent illusion. The illusion of time. According to theoretical physicist Carlo Rovelli, time is an illusion. Our naive perception of its passage does not correspond to physical reality. In fact, as Rovelli argues in The Order of Time, much more is illusory, including Isaac Newton's image of a universally ticking clock, even Albert Einstein's relativistic space-time, an elastic manifold that distorts so that local times differ according to relative velocity or proximity to a mass, is only an effective simplification. So what is Rovelli really up to? He postulates that reality is just a complex network of events, onto which we project sequences of past, present, and future. The entire universe obeys the laws of quantum mechanics and thermodynamics, from which time emerges. New type of quantum time order. One of the basic principles of quantum mechanics is quantum superposition, in which a particle exists simultaneously in two or more states. In an article published in the journal Nature Communications, University of Queensland physicist Magdalena Zeik and colleagues show that particles are not the only objects that can exist in a state of superposition. Just like time itself, the sequence of events can become quantum mechanical, said co-author Dr. Igor Pekovsky, a physicist at Stevens Institute of Technology. We looked at temporal quantum ordering, where there is no difference whether one event causes the other or vice versa. Why the block universe is a mistake. Past and future are just as real as the present. They all coexist, and you could theoretically travel there. But, argues Dean Buonumano, the interpretation of Einstein's theory may have more to do with how our brains evolved to think of time in ways similar to space than with the nature of time. Our brains transform the blooming, buzzing mess of raw data that hits our sense organs into a convincing model of the external world. It endows us with language, rationality, and symbolic thought, and in the most mysterious way, it endows us with consciousness. Or more precisely, it endows itself with consciousness. But on the other hand, the brain is also a rather weak and faulty information processing device. When it comes to mental numerical computations, the most complex device in the known universe is embarrassingly inept. The flow of time in a timeless universe. If you were to stand outside the universe, outside of space and time, and look at your life, you would see your birth, death, and every moment in between as separate points. From this point of view, time does not flow, but is static and fixed. This view of the universe may seem strange, but for many physicists, It's the one that best fits current theories of space and time, such as Einstein's theory of general relativity. In this block universe, as it is called, past, present, and future are all single points, and our perception of time flowing from the past to the future is just an illusion. However, not all physicists agree. Just because we don't know what the future will look like doesn't mean, to some, that it doesn't exist. Just as not knowing what's on the other side of a building doesn't mean that there's nothing there. And other physicists think that each now leads to multiple universes, the so-called many-world scenario. Where does time come from? The passage of time is an illusion, and there are not very many scientists and philosophers who would disagree. To be quite honest, when we say that something flows like a river, we mean that an element of the river at one moment is at another place in a previous moment. In other words, it moves in relation to time, but time cannot move in relation to time. Time is time. Many people make the mistake of thinking that to say that time does not flow means that there is no time. This is nonsense. Time exists, of course. We measure it with clocks. Clocks don't measure the passage of time, they measure intervals of time. Of course, there are time intervals between different events. Time is not real. What is time, and does it flow like a river from the past to the future? Is time real, or is it an illusion resulting from the displacement of matter, shape, and properties in space? How do clocks work, and how do they measure time? So what do physicists mean when they say that time is not real? Is there a timeless theory of physics? And can we explain the creation of the universe without time? Time passes and you cannot bring back lost hours or your youth. As Einstein said, an hour passes like a second when you are sitting next to a beautiful woman, but a second feels like an hour when you are walking over hot coals. That is relativity, but relativity is not responsible for love. All this, however, must have a reason. There is neither past nor future. As Juliet waits for Romeo, time passes sluggishly. She longs for Phaethon to take the reins of the sun chariot, as he would whip up the horses and bring in cloudy night at once. When we awaken from a vivid dream, we are vaguely aware that the sense of time we have just experienced is illusory. Carlo Rovelli is an Italian theoretical physicist who seeks to bring the fascination of his field to the uninitiated. His book, 7 Brief Lessons on Physics, with its pithy, brilliant essays on topics such as black holes and quanta, has sold 1.3 million copies worldwide. Time travel. According to the block universe theory, the universe is a giant block of all the things that ever happen at any time and place. From this point of view, past, present, and future all exist and are equally real. 2 of the dimensions of this cuboid, say height and width, represent 2 of the 3 spatial dimensions of the universe. The 3rd spatial dimension in the diagram above is omitted, the length of the cuboid, and replaced by time. At one end of the cuboid is the Big Bang. At the other end is the very last moment of the universe. Maybe it's a big crunch. There is no death. Here we tell you what happens after you're dead. Seriously. Okay, it's not that serious, because you're not really going to die. To lay the groundwork, let's summarize the scientific view of death. Essentially, you drop dead and that's the end of everything. This is the view held by intellectuals who pride themselves on being stoic and realistic enough to avoid the cowardly flight into Karl Marx's spiritual opium, the belief in an afterlife. This modern view is not cheerful, but our theory of the universe, called biocentrism, in which life and consciousness create the reality around them, has no place for death at all. To fully understand this, we must return to Albert Einstein's theory of relativity, one of the pillars of modern physics. Before we ask if time is real, let's look at what we really mean. In science, truth is a necessary component of a theory that accurately explains our observations. For example, quarks are real, but not because we can see them. We cannot see the quarks that make up protons, nor can we see the energy tracks that protons create when they collide. We can only see the effect of these tracks on the detectors, like speckles in your eye after looking at the sun. Quarks are real, however, because we can only explain the behavior of protons that collided in the Large Hadron Collider at CERN by assuming that quark particles exist. In this context, time is real in relativity because this is necessary for the theory to work properly. But can there be a theory of physics that does not need time? Can we explain the creation of the universe without time? We have to be careful when we ask these questions. We are not alone. NASA proves existence of extraterrestrial life. What kind of a stir such a headline would cause on our home planet? We can only imagine. As we know, no one has yet confirmed the existence of our extraterrestrial neighbors. Despite this, or rather because of it, researchers are still working at full speed on the search for new, potentially habitable exoplanets. But how do experts actually manage to add these exciting distant worlds to the star charts? Have celestial bodies that are basically considered life-friendly places already been discovered? And what future lies ahead for this exciting branch of space exploration? The search for alien worlds. As of June 2nd, 2022, we know that there are 5,035 exoplanets in 3,775 different systems in the vast expanses of space. In addition, there are 8,975 exoplanet candidates whose true identities have yet to be deciphered. The exciting thing, the galactic dark number exceeds the so far identified celestial bodies by a multiple. Accordingly, some astronomers suspect that there are hundreds of billions more exoplanets in our own Milky Way alone. Before we take a closer look at the exciting work of the researchers, we should first clarify a basic concept, that of the exoplanet. As the name of these celestial bodies suggests, they are planets that are gravitationally bound not to the Sun, but to another star. Most exoplanets discovered so far are in a comparatively small region of the Milky Way. In a galactic context, the word small still means gigantic. The corresponding systems are sometimes thousands of light years away from our solar system. To put this into perspective, a light year is the distance that light travels in a vacuum within 1 year, 5.88 trillion miles. Our closest known neighbor, the exoplanet Proxima Centauri b, is about 4 light years from Earth. Thanks to the Kepler Space Telescope, we now know that there are more planets in the Milky Way than stars. However, since there are huge distances between us and these extrasolar worlds, experts have to find creative ways to identify these seemingly tiny objects. The basic rule is that only very few exoplanets have been detected directly. Other approaches, on the other hand, appear far more promising. These include, above all, the so-called transit method. By 2019, this indirect detection method had succeeded in detecting 80% of all exoplanets known to date. However, the scientists do not focus on the actual planet, but rather on the changes in brightness that it causes on its journey around its parent star. In order to exclude random events, researchers must detect at least 3 transits with the same time interval between them. The analysis of the brightness curves not only reveals the mere existence of an alien planet, but also gives us an insight into some of its basic characteristics. In addition to information on the orbital period, this includes insights into the orbital distance between the star and the planet, as well as data on atmospheric composition, retroreflectivity, and temperature. Other methods. Another proven tool of astronomers goes by the name of radial velocity method. Basically, a star and a planet move under the gravitational influence around a common center of gravity. Since the host star has a significantly larger mass than its planetary companion, it travels much smaller distances. In this process, the glaringly bright celestial bodies are in turn influenced by the gravity of the planets orbiting around them. Seen through a telescope, this influence is reflected in a shift of the light spectrum. If the star moves in the direction of the observer, it appears shifted in the direction of blue. However, if it moves away from the observer, it shifts to the red. In addition, researchers have at their disposal the astrometric method, the time of flight method, direct observation, and the gravitational microlensing method, among others. The latter detection method is particularly interesting because it's based on a fascinating phenomenon, the so-called gravitational lensing effect. In the astronomical world, this refers to the deflection of light by large masses. Basically, the light of an apparently more distant source is influenced by an object in front of it. The closer the light rays pass the deflecting mass, the more they are deflected towards the mass by such a cosmic lens. Thus, experts are able to detect distant celestial bodies that would otherwise elude our interested gaze. However, a gravitational lens is not capable of creating a real image. Instead, the light distribution created in this way resembles something called caustics. Candidates and confirmation. As mentioned at the beginning of this article, almost 9,000 celestial bodies currently have the status of exoplanet candidates. In fact, it's possible that a supposedly extrasolar planet can turn out to be a false positive during the detailed analysis. An exoplanet is not officially confirmed until it has been verified by 2 other telescopes after its original discovery. That the list of candidates is so much larger than the list of confirmed exoplanets is mainly due to the fact that time at the telescopes is an extremely precious resource. In addition, an enormous amount of computing time is needed to detect the galactic objects of interest. Because of this, the experts always fall back on the help of dedicated amateurs. Many interested amateurs have made it their business to search the information provided by NASA, and some of them have even succeeded in discovering previously unknown exoplanets. The question of habitability. The search for new planets is always subject to an exciting question. Is the corresponding celestial body possibly habitable? And even more, could life already develop on one of these strange worlds? The sobering news first. Currently, the possibilities for the classification of a potential habitability of distant planets are still quite limited. However, an important indicator that astronomers can fall back on during their work is the spatial position of a celestial body. In detail, this refers to the habitable zone. This describes the distance range in which a planet must be located from its original host star, so that water can exist there in a permanently liquid form. It is well known that the presence of liquid water is a fundamental building block for the development of Earth-like life. However, the location of a planet within the habitable zone does not necessarily mean that it is habitable. Some further factors, like the orbital eccentricity and the properties of the central star, have to be considered. Accordingly, the habitability of systems around red dwarfs is hotly disputed. This has the background that these smallest stars, in whose center hydrogen burning takes place, tend to have immense radiation outbursts, which can impair the habitability of a planetary companion significantly. In addition, geological factors are also likely to play a major role in this regard. Above all, the concentration of the radioactive elements uranium and thorium decides whether a celestial body can serve as a cradle of life or not. Experts hope to achieve new milestones in the determination of atmospheric properties during future missions. In fact, experts have already succeeded in detecting water vapor on several extrasolar planets. Among them is Gliese 1214b. Gliese 1214b. Added to the star charts in 2009, Gliese 1214b is a so-called extrasolar super-Earth. Contrary to the first assumption, this official designation does not give any information about the potential habitability of a celestial body. It only refers to the mass of terrestrial exoplanets. In order to prevent irritations, it should be mentioned here that the designation terrestrial, in the case of exoplanets, does not refer to the Earth. In fact, this term simply describes rocky planets. But now back to GJ 1214b. It's located about 48 light-years away from our terrestrial home, where it orbits a red dwarf that is about 200 times fainter than the Sun. The average distance between planet and host star is again 0.014 astronomical units. As a reminder, this astronomical unit of length corresponds to the approximate mean distance between the Sun and the Earth, and thus measures about 9 million miles. The data collected by Hubble suggests that the atmosphere of the celestial body may consist mainly of water vapor. Because of this, some scientists even believe that we could be dealing with an ocean planet. This class of planets, whose surfaces are completely covered by water, exists, however, at present exclusively in theory. Exciting discoveries. Kepler 186f is only one of many confirmed exoplanets that orbit their central star within the habitable zone. Although the mass of the celestial body has not yet been precisely determined, it's considered conceivable that it's a rocky planet. The same applies to Kepler 452b, which was discovered in 2015, but this object has not yet advanced beyond the status of an exoplanet candidate. Sometimes it's not the actual planets, but their natural satellites that become the focus of interest in the question of habitability. What is true for the subglacial oceans of Europa and Enceladus may also be true for the potential moons of Kepler 1647b if they are detected one day. Finally, a brief but exciting piece of information. You will have noticed in the course of today's video that the exoplanets discovered so far have extremely cryptic names. But why is that? What sounds to us sometimes awkward and confusing follows in reality a basic naming system for the cataloging of thousands of celestial bodies of enormous importance. Thus, the first part of the name refers to the telescope with which the exoplanet was discovered, or its central star. The number indicates the order in which the host star was cataloged. The lowercase letter tells us where the planet was found in its native system. The first discovered planet is always called B, and the following C, D, E, F, and so on. If within a system several exoplanets are found in one blow, then the lowercase marking refers to the location of the celestial bodies. The innermost planet receives the B, and the following one the C. If we would transfer this scheme to our terrestrial homeland, then our planet would not be called Earth, but Sun D. Your opinion interests us. What do you think about the exciting search for new galactic worlds? Write us your thoughts, your suggestions, and your feedback to today's video in the comments. Are you in the mood for more exciting contributions on the topic of outer space? Then take a look at the other videos on our channel, which you can access by clicking on one of the images in the credits. Thanks for watching, take care, and we'll see you next time.